All right, well, hello everybody. Here we are again, finishing up chapter 4, and this video will be on variability. So again, we've already talked about central tendency. Hopefully you've already listened to that lecture, and now we will talk about measures of variability. The idea of variability is extremely important in psychology or in research in general. Most of the questions we have in research are actually about variability. And what does variability mean? It means scores are variable, scores vary, scores are different. The question is, why are people's scores not the same? So if I'm doing a study, let's say, of the GPAs of students in Miramar College, my question is not really about central tendency, which is what's the average GPA of people going to Miramar College. My research question is more about variability. Why do some people have higher GPAs than others? And you can think of lots of reasons why. Study habits, or the types of class they take, or are they also going to work as well as school? How motivated they are, all sorts of things. Their nutrition, their sleeping, all of those things could impact why people have higher GPAs than others. And that's really my research question, is to figure that out and use that information to help others. How can we optimize GPA levels in college students at Miramar? All right, or if we have questions or doing research about individuals with depression, our question is really, why do some people have higher levels of depression than others? And it can be biochemical, it can have to do with brain chemistry, it can have to do with life stress, it can have to do with social support. You can think of lots of reasons why some people may have higher levels of depression than others. So this idea of variability is key to most of our research that we do. And when we talk about measures of variability, and variability is again a descriptive statistic technique, we are going to come up with a number that tells us how closely people's scores are in your sample, how close everybody's scores together, or how spread out the scores are. Okay. So if, which is not the case, I was doing a study on GPAs in people in Miramar College, and I sampled 100 people, and every student either has a GPA of 2.9 or 3.0. That's it. There's no other scores. Everybody either has 2.9 or 3.0. In that case, we would say that the amount of variability is quite small, because everybody has either 2.9 or 3.0 as their GPA. In reality, of course, GPA is much more variable, and so if I were to get a sample of 100 students, they would probably range from, who knows, 4.0 to 2.0, or even lower than that, and you have a range of scores which would represent high variability. And this is a descriptive statistical technique because, again, you are coming up with one number. It's a summary number that tells us about the variability in the data set. And then when we are describing data sets, we usually give both. We would say the mean of the distribution is something, and the standard deviation is something else. Those two numbers kind of go together to describe the shape of the distribution. So central tendency, which we talked about, mean, median, or mode, tells about the central point in the distribution, and variability tells us about how scattered those points are around the central point. And those are the two measures that we use to describe our distribution of scores. So variability, as I said, is our way of describing how much spread there is in a distribution of scores, and we have three measures: the range, the variance, and the standard deviation. I'm going to go through them all with you. The range is the one that gives you the least information. It's kind of like the mode, and is the least commonly used. Standard deviation is the most commonly used, and you'll see that variance and standard deviation are very closely related. Once you've calculated the variance, you only have one more step to go, until you get to standard deviation, and we'll talk about how to do that. I might suggest at this point, if you have a calculator, you grab it because I want you to try to work some of these problems out along with me. In all the cases that we do, variability is determined by measuring the distance between scores, and that's what we're talking about. How far or how close all the scores are. So we'll start with the range, and the range is simply the total distance covered by the distribution, highest score to lowest score. So it's very easy to compute. For the range, you find the highest score, and you subtract the lowest score, and that's your range. So if the highest score in a distribution is 10, let's say we're looking at a quiz where people can, it's a 10-point quiz. If the highest score someone got was a 10 and the lowest score someone received is a 1, 10 minus 1 is 9, the range is 9. Pretty easy to compute. Examples of range, let's say in test scores, we have a score, the lowest score in the class was a 23, the highest score was a 98. So highest minus lowest is 75. The range is 5. Same with incomes here, 76,500 is the highest, minus 15,300 is the lowest. There's your range of income, 61,200. And temperature, you see this even during the day, like the high temperature of the day was 85, the lowest temperature was 62, 85 minus 62, or a range of 23 degrees. So while this tells us something about the distribution of scores and the variability, it only considers extreme values. So the only two numbers you're looking at are the highest score and the lowest score. And sometimes that's not very representative, like in test scores. Maybe I did get someone who had a 23 and someone who had a 98, but most people scored in the 80s. Most people got like an 80 or an 82 or an 83. And even if the majority of our scores were there, 95% of people got an 80 or an 85 or something like that. But I've got one very low score and one very high score. It makes our range seem large because, again, we're only looking at the extreme values. So while it's useful to some degree, it's not the measure of variability we use the most because it only considers extreme values. Which brings us to the standard deviation. You have probably heard this term before, standard deviation. May not know exactly what it means, probably have never had to compute it, and that's what we're going to do today. So the standard deviation, what does that even mean? Standard really means average, and deviation means distance. And so what we're talking about is the average distance between a score and the mean. And you'll see how we compute this. So the standard deviation is how far on average is any one score in a distribution from the mean. If you have a small standard deviation, it means you have a lot less variability. It means that all the scores are very close to the mean. And if you have a large standard deviation, it means you have a lot of variability. The scores can be quite distant from the mean. Calculating standard deviation is a process. It is simple math. You'll see as we go through it, the math is not hard. You just have to remember the steps. And I have this written down for you, so if you want to pull up my PowerPoint and look at this, you can look at the formula as well as the words here, as well as here it is also described for you. But I think the easiest way is to just do it, and I think it would be great if you could follow along with me as we do this. So here we go, calculating variance and standard deviation. Step one is to calculate the mean. Well, we've done this before, and I'm sorry, it looks like my slide is a little off. These are the scores. They should be under here. We have 5 participants in this study, and we gave them a mood questionnaire. How is your mood today on a scale of 1 to 10? And so person 1 got a mood score of 6, and person 2 got a mood score of 8. Person 3 got a mood score of 8, etc. So step 1 is to find the mean. And remember the mean, you add up the scores, which in this case is 35, and divide by the number of scores, which is 5. So the average mean mood score in this sample is 7. Okay. Next, we're going to calculate deviation scores. Remember, we're looking at standard deviation, so it makes sense we need some deviation scores. What does deviation mean? And this is important. If you can understand this concept now, it will really help you as we go farther and farther along in this course. But a deviation score is telling you how far is any one score from the mean. So person 1 got a 6 on the mood questionnaire. The mean is 7, so we're taking 6 minus 7 to get a deviation score of -1. And this -1 is telling us that this person scored 1 point below the mean, which makes sense because they got a 6 and the mean is 7. Next, we have person 2 who got a score of 8. We subtract the mean. We get a deviation score of 1. And this is telling us that this person scored 1 point above the mean. Again, that makes sense because a score of 8 is 1 point above 7. Person 3 also got an 8. We have the same deviation score. Now, what about person 4? Person 4 got a 10. The mean is 7, so 10 minus 7 is 3. And this is telling us this deviation score that this person scored 3 points above the mean. And person 5 had a score of 3 minus the mean of 7. And so that person scored 4 points below the mean. So these deviation scores are important and they're not a mystery. They shouldn't be. They're actually telling you something very useful about each score in terms of variability, how close or how far somebody scored from the mean. As you recall, we're doing standard deviation. We said standard means average, so average deviation. What do you think the next step would be? The next step would then be to find the average deviation score. And when you find the average, what do? We add up the scores and divide by the number of scores. So what happens if you add these scores up? If you do that for 1 second, what do you get? The problem is you always get a 0. And that's a problem because anytime you do this, if you do it correctly, if you add up your deviation scores, you will get a 0. And then if you have 0 divided by anything, you always get 0, and so we would never be able to calculate a standard deviation, which actually is a good check for yourself as you're working through these problems. If you add these scores up and you don't get 0, then you know you've done something wrong. Or close to 0, because if you are rounding numbers, you might get a score like when you add up the deviations of 0.0002. That's just a rounding error, but just generally this should add up to 0. All right, so since we have this problem, and it's basically because we have the negatives and the positive numbers and they cancel each other out, giving us a summed deviation score of 0, we have to do a couple extra steps. And what we do to get rid of the negatives is we square all the scores. So step 3 is to square your deviation scores. And if you recall, when you square anything, it gets rid of the negative sign. So participant 1, as you see, had a score of -1, but we're going to square it, which will give them a squared deviation score of 1. This person had a score of 1. We square it, we get 1. Person 3 had a score of 1. We square it, we get 1. This person, I believe, had a score of 3. And so we square it and we get 9. And this person, yes, was -4, which we square and get 16. So step 3 is to square your deviation scores. And there they are. Step 4, so now we're going to do the average part. Step 4 is to add them up. You add up your squared deviation scores. We call this the sum of squares. You're going to see sum of squares quite a lot throughout the semester. And the sum of squares is our shorthand term of saying you've added up all the squared deviation scores. So 1 plus 1 plus 1 plus 9 plus 16, which is 28. All right. Now, what we need to do is the last step, and this is one part you just have to remember. If you're talking about a sample, and in most cases, we're talking about running data on a sample, collecting data on a sample, and finding the standard deviation of a sample. If you're looking at sample data, you take your sums of squares, which is abbreviated with capital S, sums of squares, and divide by n minus 1, where n is the number of people in your sample minus 1. You just have to remember that that's the case. So in this case, we take 28, which is our sums of squares, and divide by 4, because if you recall, we had 5 people in our sample. 5 minus 1 is 4. And you get 7. 7 is the variance. Variance is one of our terms of our variability terms. So you have the variance here. Variance is 7. There's a slight difference if you're calculating variance for a population. Instead of dividing by n minus 1, you just divide your sums of squares by n. Capital N means total number of participants in your whole population. So the calculation, if you're looking at a sample or population, is all the same up until step 5. And when you get to step 5, if you're looking at a sample, you divide sums of squares by n minus 1. And if you're studying a population, you divide sums of squares by n, okay, which is the total number of people in the population. So once you've gotten to variance here, and in this case we're using a sample, so our variance is 7, and in no way will it always be equal to the mean. This is just by chance that our mean was 7 and the variance is 7. That will probably never happen again, just coincidence. Once you've gotten to variance, you only have one step left to go to get to standard deviation. And this should make sense, because in order to get to variance, what did we have to do to our deviation scores? We squared them. And all of our sums of squares and our variances now on this new scale of mood score squared points, because we took all the deviation scores and we squared them. And so now we're on a new scale, this squared scale, which doesn't make any logical sense. It makes mathematical sense, but it doesn't make any logical sense. Like if I were to tell you, if instead of studying mood score, we were studying IQ, and I were to say the variance in a group is 7 IQ score points squared. It doesn't mean anything. So if you remember from another math class, how do we get rid of a squared? Well, we square root. So to get to standard deviation is simply the square root of variance. We're going to take away all the squaring that we did, and get back to our regular scale, which in this case was mood score points. So we had a variance here of 7. The square root of 7 is 2.6458. And that becomes our standard deviation. And so we're saying that the average distance between any score and the mean is 2.648458. Mood score points. We're back on our regular scale. In this class also, we will always round to 2 decimal places, 2.6458. So we're always going to round to 2 decimal places. It's the convention that we use. And if you recall rounding rules, if your next number is 5 or above, you round up. And if it's less than 5, you round down. So in this case, we have a 5, so this would be 2.65. And there's your square root, standard deviation. Hopefully you saw that the math is not hard. It's just a matter of remembering the steps. And perhaps you can practice this or go back over it and take a look. Here's the formula for standard deviation. The square root of the sum of each score minus the mean, those are the deviation scores, square, and remember it's divided by n, all the members of a population if you're talking about a population, or n minus 1 if it's a sample. And you can see we symbolize variance as s squared, and we symbolize standard deviation as s. And so the square root of the variance is the standard deviation, which is just what we did. Taking a look at this slide here, if we're talking about standard deviation, and standard deviation means variability, well, which of these data sets should have a higher standard deviation? So they're both a measure of score, and again, frequency up here on the y-axis. Which one should have the larger standard deviation when you calculate it? Well, it will be this one, okay? Because you've got a wider range of scores. You've got people scoring low here all the way at 0, and people scoring all the way here above 90. You've got quite a big range of scores. Whereas in this case up here, you have much smaller standard deviation. You have less variability. Nobody scored below 10. Nobody scored above 70. This would, when you compute it, would have a smaller standard deviation. So hopefully you can see that now. Another example of groups with different variability. This is height, and again, frequency in two groups, women and men. The blue is men, and if you would imagine these bars would continue, right? It's kind of like behind the pink bars. And women here is this pink or purple bars. And by looking at these two distributions, if you were to say which one has the larger standard deviation or more variability, well, it would be men. There is more variability in the heights of men. The range is larger. You've got men down here at 55 inches, but you've got very, very tall men up here, almost 85 inches. Whereas with women, you have women down here at the 55 inch, but they don't get as tall as the men. The variability or the range ends here. The highest, tallest women are not quite as tall as the tallest men, so they've got a smaller range of scores and hence would have a smaller standard deviation. All right, symbols. So let's look at this together. Remember, we've got different symbols depending on if you're a population, looking at data for a population or a sample. We already talked about mean. The symbol for mean of a population is mu. The symbol for mean of a sample is capital M or X, capital X with a line over the top. That would be X bar. I'm not filling these formulas in. You may want to think about them yourself, but yeah, in terms of how you get to them. Sorry about that. Sums of squares, the only symbols you would use is capital S, and it doesn't matter, population or sample, there's no difference. Variance in a population is sigma, this Greek letter sigma squared, whereas in a sample it's lowercase s squared. The square part should make sense because remember we squared all the deviation scores, so we're on this, we've squared everything and therefore the symbol has the squared demarcation. And then standard deviation is, remember, the square root of variance. So when you square root sigma squared, you just get sigma. And when you square root s squared, you just get s. So that's the s is the symbol for standard deviation in a sample, and sigma is the symbol for standard deviation in a population. I'd like you to think about and maybe work on this in terms of central tendency and variability. We've got three data sets, A, B, and C. Here's the data. please try to calculate the mean of each data set, the standard deviation of each data set, and tell me which has the largest standard deviation. And the question here is it possible to answer C, which has the largest standard deviation, without actually computing the standard deviation? So as practice, it would be great to find the mean and standard deviation of all three. Pause this PowerPoint if you would at this point. And now I will go through the answers with you. So the mean for data set A, you add everything up and divide by 5, you get 9. The mean of data set B is you add up all the scores and divide by 5, you get 5. And the mean of data set C is you add up all the scores and divide by 5, and you have a mean of 9. Standard deviation, and you can look at this or pause this to see how, if your answers were incorrect, how you got incorrect answers. But standard deviation for data set A is 2.83. Standard deviation for data set B is 0. That should make sense because every score is a 5. So the average score is 5 and the standard deviation is 0. There's no variability. Everybody got the same score. So standard deviation here would be 0. And the standard deviation for data set C is 5.62. So which data set has the largest variability? That's data set C. And could you tell that without actually doing the computation? Well, yes, because data set C has the most varied, the most difference in the scores, right? Looking up here, you've got a score of 2 and a score of 15. There's quite a bit of difference there. And so it makes sense that that has the largest standard deviation. You can also do these, and again, pause if you want practice, which I would highly suggest practicing. Finding the mean for each test. This is sample data. So pause every time you're calculating, and then I will continue on. So the mean for each group is 0. Then find the standard deviation for each test. Again, pause and let yourself find the standard deviation. And when you do, I said this is sample data, but just so you can see, 3.81 is your sample standard deviation, and in this case, 15.81 is your sample standard deviation. You could try to find the population standard deviation, again, just dividing sums of squares by n, which would be 5, instead of n minus 1, which would be 4. And what does this tell us? I said you always show a mean and a standard deviation when you're describing some data. So what does this tell us? This tells us that the average, let's say these were 2 different tests. The average on the 2 tests was the same. Everybody averaged an 80. But there was a lot less variability in scores on test 1 than on test 2. There was much more variability in test 2, or test score 2. You can do the same for this one here. Find the mean. Again, pause if you want to find the mean, which I would suggest you do. The mean for test 1 here is 70. The mean here is 90. And then find the standard deviation of each one. Standard deviation here is 7.33 for the population, or 8.02 for a sample. It's the same here. So what does this tell us? This tells us that on test 1, people scored lower, on average 20 point lower than on test 2, but the variability was similar. The variability was the same. I just wanted to check if I said the right thing here. Yeah, there are 5 scores here. There happen to be 6 scores on this one. Okay. The understanding of mean and standard deviation is very important in our moving on to inferential statistics. And if you think about this with me, if the mean of a population is 100 and the standard deviation is 15. Is a score of 90 very extreme? Well, not really. The mean is 100. Standard deviation is 15. A score of 90 is not terribly extreme. But a score of 65 now is how many standard deviations away from 100? Quite a few. And it becomes an extreme score. But if the mean of a population is 100 and the standard deviation is 40, well, is a score of 90 extreme? Not at all. 90 is very close to the mean, especially if the standard deviation is 40. And is a score of 65 extreme? Well, again, it's within one standard deviation in this case. 100 minus 40 is 60, so 65 is within one standard deviation. All of a sudden, the score of 65 is not terribly extreme. So understanding the mean and standard deviation, and you'll see as we work through these, becomes very important. How about this one? On an exam with a mean of 80, you get an 85. For which of the following values for standard deviation would give you the highest position in the class? How would you, if these were the standard deviations, which one would make you feel better about your grade? Take a minute and think about it. The answer is A, 1. If the standard deviation is 1, you scored an 80. A score of 85 is 5 standard deviations above the mean. That's awesome. You did great. If you got this test had a mean of 80, you got an 85, and standard deviation is 5, well, then you scored 1 standard deviation above the mean, which is great, but not as great as 5 standard deviations above the mean. And if the standard deviation was 10, well, you still scored higher than the mean, but now you're half a standard deviation above the mean. Not as impressive. So that's how this works. I hope it's starting to make some sense. Feel free to email me with any questions, and practice, practice, practice. That's the key to statistics. All right, thank you.